Hello and Assalamualaikum everyone. In this video, we're going to move on to lecture 3 on Markovian queuing models. Okay, so two topics to be covered in the first part is the steady state condition and also the birth-death process. So previously in lecture 2, we have proved the memoryless property of the exponential distribution. So this property is also known as the Markovian property. Okay, so a discrete parameter or continuous parameter stochastic process is said to have or to be a Markov process if given the present condition of the process, the future is independent of the past and thus the process is called memoryless where it forgets its history. Okay, so usually the aim of queuing analysis is for us to determine the long run behavior of the system. We want to know whether the behavior of the system settles down or not. Okay, so this generally means we want to determine the proportion of time or the probability that the queue is in state I. Okay, so state here represent the number of customer in the system. So if state 2, basically it means we want to determine the proportion of time or the probability that there are 2 customer in the system. Okay, so for this, okay, we write, okay, the limit of the probability that the queue is in state I at time t as t approaches infinity as pi I. Okay, so that is after a long time the probability that the process is in state I is independent of the starting state. So this represents the probability that the queue is in state I approaches a certain limit as your t approach infinity. Okay, so pi I is also called the limiting probability or a steady state probability. Okay, so if the summation of pi I for all of your state is equals to 1, okay, this set of pi I is called a limiting distribution or a steady state distribution. Okay, so pi I basically represents the long run probability of being in state I. Next, we're going to look at the definition of steady state condition. So steady state condition is the state whereby the system is independent of the initial state and by the time that has elapsed. Okay, so basically it means that the system is stable and the probability distribution of the state of the system remains the same over time. Okay, so for a stable queue in the steady state, the probability of being in each state remains the same. So therefore, for each state, the rate of change of the probability must be 0. Okay, so this means that for any state I, okay, let's say you have a state I, okay, the probability of being in state I and leaving it is equals to the probability of being in state J and entering state I where J is not equals to I. Okay, so Qi here represents leaving state I to state J. Okay, so for example, let's say you have J equals to 1, 2, and 3 and you have your state I. Okay, so the left hand side here, okay, represents the probability of being in state I and leaving state I going to state J. Okay, so it must be the same with the probability of being in state J, all of state J, okay, and entering state I from all of the state J. So it must be the same. Okay, so the rate of change of the probability must be 0. So the left hand side is the green one, okay, being in state I and leaving state I, going to state J, where J is not equals to I. Okay, and then the right hand side, okay, the probability of being in state J, let's say you have J equals to 1, 2, and 3. you have three states of J. Okay, the probability of being in state J, okay, all three states of J and entering state I. Okay, so that is what it means by the steady state condition. So the previous set of equations that we discussed under our steady state condition is known as the steady state equations or sometimes global balance equations. Okay, so they can be thought of as balancing the flow of probability in and out of each state. Okay, so there are another set of equations known as the detailed balance equations. So these detailed balance equations can be thought of as balancing the flow of probability between any two states. Okay, so the global balance equation is balancing the flow into and out each state. Okay, while the detailed balance equations is balancing the flow between any two states. Okay, this equation state that the flow of probability from state I to state J is equals to the flow of probability from state J to state I. Okay, so by looking into our previous example where we have J equals to state 1, 2, 3, so the detailed balance equation represents the flow between any two states. So from for state I and state 1, and then for state I and state 2, and then state I and state 3. So it considers the flow separately between two states. Okay, where the global balance equation consider the flow of probability in and out of each state. Okay, for example, this is in and out from state I, okay, to other states. Okay, all of the states J. Okay, so the detailed balance equation just consider the flow of any two states. Okay, so solving the detailed balance equation basically means that the solution also satisfy the global balance equation. So how to show that is just by summing over J on both sides. So solving this, okay, basically means you should also satisfy your global balance equation. So next we're going to look at the steady state solutions. Okay, so in order for us to solve the steady state equations to find the solution, okay, usually, okay, the steady state equations are often written in matrix form. Okay, first let us define matrix Q, okay, to be the rate matrix or sometimes just known as the Q matrix, where its diagonal elements, okay, represents the negative value of sum of the rate leaving state I. So this is for the diagonal element for matrix Q. Okay, so the sum of all rate leaving your node I, okay, so the negative value of the sum will fill up the diagonal element of matrix Q. Okay, and the off diagonal element will be represented by the rate of jumping from state I to state J for I not equals to J. Okay, the detail of this, how we're going to construct matrix Q, will be discussed later when we move on to our specific model. Okay, so next we're going to define our column vector pi, okay, where it is equals to value of probability of being in state I for all I. Okay, this is a column vector. Hence, we can write our steady state equations equals to pi transpose Q equals to 0 transpose. Okay, the sum of each row of Q is equals to 0. Okay, to represent the steady state or balance condition, right? So in order for us to solve the steady state equations, we need to keep this equation in mind. Okay, pi transpose times Q matrix or rate matrix is equals to 0. So this is initially a column vector. So you transpose, you get a row vector. Okay, so the value of 0 here is also row vector depending on the total number of state in your system. So before we move on to our next section, let us first take a look at some of the general results and notation that we're going to use in describing our queuing model. So previously, we have learned about the expected number of arrivals per some unit of time, or the mean arrival rate lambda, and also our mean service rate mu. Okay, so the more general type of notation for this particular rate is known as, or denoted as, lambda I, where it refers to mean arrival rate at state I. Okay, state I represents the number of customer currently in your system. So if you are currently in state 2, basically it means you have 2 customer in the system, and lambda 2 refer to the mean arrival rate when you already have 2 customers in the system. Okay, so the same goes to your mu, but your mu refers to your service rate. Okay, so 1 over lambda refers to mean inter-arrival time, while 1 over mu refers to your mean service time. Okay, so C is going to represent our number of server in our system, so how many server we have in our system, and rho is going to represent the ratio of traffic intensity equals to lambda over C mu. Okay. So basically, when the value of your rho is greater than 1, okay, the steady state condition cannot exist because the queue will keep on growing. Okay, because the average number of arrivals into the system basically exceeds the maximum average service rate of the system. Okay, unless a potential customer is stopped or restricted or not allowed to join the queue anymore, the waiting line will keep on growing. Okay, so for a steady state condition to exist, the value of rho must strictly be less than 1. Okay, however, this still depends on the condition of the waiting line, whether it is a finite waiting line or finite queue or infinite waiting line, okay, where there are no restriction on the number of customers that can wait in the line. Okay, regarding the value of rho, we will explore more further when we move on to our specific type of queuing model. Okay, so these are some of the notation, okay, with regards to the performance measure. Okay, first is pi I. So pi I represents the probability that there are I customer in the system. Okay, L, okay, the first performance measure refers to the average number of customer in the system. So usually when we analyze our queuing model, we want to know the average number of customer in the system per some unit of time, let's say per hour or per minute. Okay, and LQ refers to the average number in the queue or in the waiting line, how many customer wait in 1 hour, for example. Okay, and W refers to the time. Okay, so W average time spent in the system by a customer. Okay, and WQ average time spent in the queue waiting for service. Okay, so in the system basically includes waiting in queue and receiving a service. Okay, the same goes here. Okay, average number of customer in the system refers to the customer waiting plus the customer currently being served, right? Okay, so the value of L and LQ is calculated using this formula. So L refers to average number of customer in the system. Okay, so basically we want to find the average. So we take the value of I and then sum up, okay, your I pi I for all I, for all of your state, because it refers to system. Okay, but for LQ, since it refers to the number of customer in the waiting line, so we're going to take only the value of the customer waiting. So I minus C. So C is the number of server, okay, which refers to the number of customer currently being served. Okay, so the number of customer waiting is your total number of customer minus the number of customer being served by your C servers. So then you will get your value of LQ, which is the average number of customer in queue. Okay, So the relationships between your L and W, okay, under a steady state condition, so this equation holds. L equals to your lambda bar W, and also LQ equals to lambda bar WQ. So this relationship is built based on the relationship built by Little's queuing formula. Okay, so this part is discussed briefly under section 3.1.4. So this is one of the most powerful relationship in queuing theory developed by John Little in the early 1960s. Okay, so lambda bar refer to your arrival rate. Okay, refer to your arrival. So this also depends on whether the type of waiting line is infinite or finite. Okay, so then, so under the steady state, under the assumption that the mean service time is a constant, so the value of W, which is your average time spent in the system, is equals to WQ, which is average time spent in the queue plus your 1 over mu, which is your mean service time. Okay, and if you multiply both sides, with your lambda bar, you should get this equation. Okay, so if you multiply this with lambda bar, so you have lambda bar W, which is equals to L, and this right hand side also with lambda bar, so you will get your LQ here and lambda bar over mu. Okay, so lambda bar here is a general notation of the lambda. Okay, as we go on into a more specific type of queuing model, then we will see on more specific way to calculate our lambda. So that is all on some general results and also a little bit on Little's queuing formula.